Thank you all for joining. My name is Karim Mastoud. I am the Manager of International Projects at Premier Corex. I'd like to welcome you to joining this session. If you have joined us before, thank you for joining. If this is your first time, welcome. We hope that you'll find this useful and beneficial. Today we are joined by our colleague Leigh Wright. Okay. Leigh, could you scroll in, please? Next slide. Okay. So Leigh is going to be talking about shut-ins, insights from the North Sea case studies to minimize formation damage and maximize production. Thank you for joining. So this is your key takeaways from the session, which I trust you will find very beneficial and informative. Okay. Next slide, please. Okay. So quick housekeeping rules, please. Please use the Q&A panel to submit your questions at any time. The presentation is expected to run about 30 to 40 minutes, and then we will take questions at the end. Okay. And we are recording the session. If you will get a copy of the recording once this is done. Okay. And the audience are all muted. Okay, so thank you for any questions that you might have. Just post that through the Q&A session. Okay, and this is just a quick bio about Leigh, our speaker for today. So he's a business development and technical advisor at Premier Corex based in Aberdeen. He's over 11 years of specialist experience in information damage. Leigh has co-authored multiple SPE papers, information damage, and he's managed and delivered more than 100 formation damage projects worldwide, including the Norway, UK, India, UAE, Oman, West and East Africa, and Indonesia as well. He's a geologist by background, and he has experience in petroleum geology and petroleum geochemistry, and he has a bachelor's degree from Aberdeen and multiple degrees from Aberdeen and Newcastle University. So Leigh, thank you very much for speaking today, and over to you.
Thank you very much. Hang on 2 seconds. There we go. Yeah, thank you all for joining today. Today we're doing a webinar on formation damage laboratory testing for shut-in wells. So quite a topical topic for the moment, given what's going on in the world. But we'll start off with just a run through of why wells could be shut in, what we look at in the laboratory, and why analytics are important. So the main reasons for shutting in wells could be batch drilling. We've got a case example, a case study for that as the second case study. Maintenance, there may be something that requires to be fixed, so the well gets cut off for a while whilst the work's done, keep everyone safe. Economics, oil price might not be favourable to the well being produced. Maybe the surplus, there's too much surplus on the go, the oil price has gone down too low, you want to keep the price higher. And then geopolitics, which as we all are aware in the news, there is certain conflicts ongoing in the world at the moment where wells may have to be shut in due to danger to the fields or danger to the employees. So, yep, that's quite topical. So why is shutting in the well important to test in the lab? We obviously are, when a well's shut in, the temperature and pressure downhole doesn't change, so you're basically cooking. You might have fluid redistribution without the underbalance producing out or anything getting injected, so you might have fluid redistribution, saturation changes. Might have fines settling out, they might have been mobilized and would have been potentially produced through the wellhead and produced out, but then now with being shut off and settled down, they might settle into the pore throats in the network, and when the well's restarted, they might not be able to be remobilized. They might cause a barrier to flow, which means that the production won't be as good when the well comes back online. You also, if you're having an extended period of shut-in, then the chemistry might start taking into effect. You might have, because you're settling out, you've got nucleation sites. You might have scale starting to form. You might have some organic deposition, maybe some waxing might fall out, because obviously when flow is occurring, everything's mobile, you doesn't have the time to settle out. So as mentioned at the start of this slide, today's focus on laboratory testing from a formation damage point of view. I'm not an engineer, so I won't go into too much of the completion sides, etc. on that. But yeah, creating understanding, pre-planning shut-in wells and restart strategies avoids unnecessary intervention costs. So obviously, planning is key. If you are going to batch drill, for example, then understanding what will happen with the fluids are going to interact with the near wellbore is important. Understanding that if intervention is going to be needed in early life, you might want to acidize that. But what is important is that you understand what's going to happen when it comes back on. You don't want to turn the tap back on after waiting 9 months, 12 months, 2 years, and then have to shut everything down and go in with a treatment to stimulate. So yeah, poor planning, that means that you may have to spend more money in the future, which is not economic. You again stop production again, you don't generate that revenue. So understanding if behavior is not understood, then you might have mechanisms that are going undiagnosed. The treatment could be wrong. For example, if the well comes back on and is not producing correctly as expected, you might think that, well, that might be related to the mud. So you go in with a treating agent to try and dissolve the bridging agents or the base, the solids of the candidate drilling fluid, where actually it could be scale that's formed. So you would need to go in with a different treatment solution. And also, that might not be able to be fixed. So the production losses may actually become permanent. So yeah, it's really important to make sure that these are planned and understood. Obviously, when we're talking about the geopolitical risks, this is maybe something that you can't mitigate against. But whilst things are shut in, you can always carry on and check later on whilst the well's shut in before you start using mimicking what you've done before. So again, what is important in terms of testing in the lab? The reservoir core material is available, prepared and selected correctly. What is key here is when you're doing different areas of shut-ins, which I'll speak on the next slide, is that you have the correct core. That way you can understand the geology, making sure that the right analysis is done at the start of the project or the start of the campaign. Like XRD, for example, is key to understanding what fines are there, what quantity are they swelling or are they mobile? Are they going to settle out? The pressure and temperature is extremely important, mimicking that correctly in the lab. A few degrees temperature difference could have a massive effect on the chemical reactions. So you might have polymers that don't break down at a certain temperature, but they break down at a higher temperature depending on what type of fluid you're using. If you're mimicking that in the lab and you choose to go with a lower temperature than is representative, then you might not get the correct chemical reactions in the shut-in test. And that again gives you a false narrative of what's actually going to happen. So again, as in all formation damage testing, you want to mimic as closely as possible to the reservoir temperatures and pressures, because the chemistry is really important. So for current and historical wells, for example, there's in Libya, there's been a lot of wells that have not been reactivated. So the key for a historical well or a current well that's been shut off is to understand what's been done previously. So make sure that the well history, the drilling reports are understood. You're looking to see what fluids have been used downhole. If they're still available on the market, then you'd want to test them in the dynamic part of the shut-in testing. And therefore, you would then shut in the samples, replicate a standard period of time with the correct chemicals, and then you find out what is causing the damage mechanisms. So post the shut-in test, then you can correctly attempt to treat in the laboratory the mechanisms that are potentially causing any production issues. And on a positive note as well, we might not always have formation damage. Everything might clean up perfectly. So understanding that is important as well. And for the current and historical, if there's reservoir core still available, that's key to have that provided as well. So on the right-hand side of the screen, you'll see that there's a base parameters table from a project where we had shut-ins with a reservoir core. These were taken from a preserved sample. The A's and B's are slightly different lithologies, different geological content. So the red samples were knocked out of contention from the study for various reasons. Using CT scans, they weren't deemed homogeneous enough or matching the reservoir core. The samples in orange were chosen because they're the closest parameters to each other for the shut-in testing. So if you're doing a standard shut-in procedure, you might want to look at a 1 month shut-in, a 3 month shut-in, a 6 month shut-in. And if you're doing various length of shut-in timings, then each core sample should be as comparable to the other one as possible. I know that may be sometimes geologically impossible with the core material it's taken, because core is variable, but matching as close as possible to each other gives the timings the best chance to show what's differentiating between the periods of time that are being chosen to replicate the live shut-in period of time. So that's just a very, very proper housekeeping moment, is to make sure that the samples are as comparable as possible. Diagnostics is really important as well. As you may have heard in previous presentations, or if you've worked with us in the past, it's important to understand what has occurred to give the best, be able to diagnose the best solutions for any treatment if there is any issues. So what's causing the alteration? Why is things not coming back online the way they should? The micro CT scanning, which is in the bottom right diagram, shows you where any issues, any reduction in permeability would be happening. Also, if there isn't any reductions occurring, it gives you an understanding of how things have cleaned up. Using the images from the micro CT, you can identify where things are happening, and using dry SEM, looking at the solid damage. So there may be, depending on the resolution of the micro CT scanning, you might see some fines agglomeration if it's high resolution. Also, if the solids from the drilling fluid have gone deeper into the reservoir, have they settled? Have they been able to be back produced? And as we were mentioning earlier on, what's happening with the compatibility of the fluids, has there been scale forming? So cryogenic SEM allows you to see everything that would be removed in solvent cleaning. So for example, if there's any salt precipitates formed due to any interactions, any fluid incompatibility forming with maybe potential separation of the drilling fluids over time, if it's a high temperature, long-term shut-in, the cryogenic SEM will have the power to allow you to understand the impact of that along with all these. So in the best case scenario, you combine all three of these diagnostics to understand the mechanisms that are occurring. And in the first case study, that actually turned out to be a really powerful tool. As that was mentioned, onto the first case study from the North Sea. We're looking at a siliclastic reservoir, new wells. As mentioned before, we have reservoir preserved samples, allowing multiple cores to be taken from each, and there's 2 lithologies, so 2 preserved samples. So when we're doing that, we manage to take many samples from each of the preserved, and when we're running the base parameters, we manage to integrate with the client to make sure that the samples were brother and sisters. The case study will show that the drilling fluid was analysed first. So in the lab, they did a drilling mud application followed by a drawdown to see how the mud interacted with the core to give a base case. That sequence then was built up to include a displacement fluid. So again, that's showing that the mechanisms that are reducing perm with this drilling fluid on its own, and then the drilling mud displacement. So once you've identified those mechanisms in the two base case core floods, you then can see the effect of the 3 months. So you're knocking out the variable of the drilling mud. You understand how that's interacting with the reservoir core. You're understanding how the drilling fluid and the displacement fluid are interacting together and interacting with the core. So when we move on to the shut-in, the only variable we're looking at comparing to those two tests is the effect of the shut-in period time. So that was, in this case, 90 days or 3 months. So moving on to the results, for those who are unaware, the scale on the x-axis is going from 0 to 100% regained perm. The drawdown rates used were 2, 5, 10, and 20 mils a minute. So we're doing step drawdowns. That's represented by the colors next to the drawdown rates. The top column is the mud on its own. So you can see going through that one, the mud at the first drawdown with 2 mils a minute actually regained around about 40% of the permeability. So that's a 60% drop. And you can see as the rates were ramped up, there was some more cleanup. So when we added the displacement fluid, you can see that that first rate didn't clean up as well, but it got to the end, you had a maybe 15 to 20% drop. So then on and I should have mentioned at the top, the top three are the high perm samples, the bottom two are low perm samples. So as you can see, the poorest performing in the high perm samples was the shut-in after 90 days. It only regained 45%. You can see on the low perm sample, the displacement fluid sequence included with the 90-day shut-in. Again, that only regained about 45% as well after all three drawdowns. So if you were looking at this from a point of view of turning back on the well, if you had just been in the base case, you're looking at potentially 60, 65%, 70% regained perm comparing to 45. So you're not getting that much. You're losing production from shutting it in for 30 days, just on the drawdown data alone. So the next step was in the sequence was to offload the sample from the test cell and remove the operational fluid cake body. As you can see in the mud only, with no shut-in, that had about the same effect as a drawdown after about 20 mils a minute. But what you can see, especially in the low perm sample that was shut in for the 3 months, you can see that cake had taken that cake, took it right back up into the 60-65% return perm zone. So that, in terms of lab data alone, indicates that the external cake got baked and was harder to shift. And then I think this is for this part of the case study, I think this point is quite key. For those that are unaware of what spin down means, the samples are put into an ultracentrifuge and spun. And yes, you cannot spin down your reservoir interval, but what this replicates is long-term production. So the good news in this case study was that when the samples were spun down, you're actually getting up to 80 plus return perm. So what this indicates to the operator in this scenario is, although you may have initial poor production compared to prior to what was expected after shutting in, or if you were not shutting in, but after a long term of production, you should start cleaning up that operational cake that's been baked a little bit onto the surface. The fluids that are stagnant in the pore throats start getting mobilized, and that means that after a long term in shut-in, you get back to what production was expected. So at the end of the day, this showed that yep, okay, we're going to have an initial issue, but producing for the life of the field, it should get back to what it's expected to be. And here we have the pressures relating to the drawdowns. You can see the keys on the sides with the different rates. And you can see in the low perm sample with no shut-in that the differential pressure was quite low. And that's the bottom left graph. You didn't need too much pressure to with those rates to initiate the cleanup. But on the 3-month, the pressure generated by those flow rates to push that cake off was generally a lot higher. And again, that's indicative of the cake having been cooked. I know there's a lot of cooking references here, but the cake's been cooked, and then it takes a little bit of that short period of time to push away, and then it does stabilize at a slightly higher pressure at low perm. So again, this information is quite key to understanding what will happen in the field when the taps are turned on. So you're expecting that initial kind of barrier, the bit of pushback, and then once things get going, it should flow back to normal. As you can see, as throughput commenced through to the thing, the pressure stabilized, and then flow was continuous. So again, a very good data point to have. And just so we have a little bit of an understanding, we've got some images of some cakes here that were presented. You can see the 3-month cake has had more of an impact, but it's just to give a bit of a visualization of what we're actually talking about in terms of drilling fluid cake. So on to the analysis. We have the micro CT scanning. I believe that most people on the call should be aware of the micro CT from the previous webinars, but what we do here is we scan the sample prior to testing and post drawdown. So we remove the cake and do the spin down at a later point. So what we're left with is the density change, the alteration. And on these images, the orange color, the orange-red color is the higher density, and this is accumulation. So you can see the cakes on the top of the samples. The white dots represent the cylinders. So you can see on the left-hand side, we've got the high perm with no shut-in, the high perm with 3 months, and then on the right-hand side, the low perm and the 3-month low perm. So what these are indicating is that we have infiltration into the near-wellbore in the top half of the high perm sample with no shut-in. But in the 3-month in the high perm, we've actually got a lot more solids infiltrating into the near-wellbore. So what this shows us is that these solids have been potentially cooked in, and maybe there's been some deposition, and then they're harder to remove after the 3 months. You can see also a little bit difference in the cake. And then on the low perm, you've got kind of the opposite occurring. You can see that there's a lot of infiltration with the low perm not being taken out with no shut-in, but then after 3 months, we actually don't have as much solid particulate in the core sample. So what's important in the high perm samples was when we were looking at that, you can see, as I've said, that you've got a lot more particulate density change showing up in the 3-month. So we had a little look under the dry SEM imagery. You can see the wellbore face was pretty blocked. This is basically a standard drilling mud test. The pore sizes were reduced from 28 to 8 microns. You can see on the right-hand side, the cryogenic SEM indicated that there was operational fluid filtrate retained in the core, probably with remnants of the drilling solids. And yeah, you can see the pore throat sizes were reduced 28 to 22. So you can understand why the permeability has been reduced. But I think the image in the bottom right corner of the screen is really key to why the shut-in gave great information, specifically in the high perm, is that bridging polymer over the operational fluid constituent over the pore throat has happened that was not seen in the no shut-in test. So what that indicates, after 3 months, without cleaning up the pores with the drawdown return to production, you're actually generating additional damaging mechanisms that are not seen when the sample's not being shut in. So that is causing the reduction in perm, and that is the major difference in takeaway you have. So for this case study, long-term production will get back to what's expected and match the no shut-in time after a period of time. But also there will be some mechanisms related to the mud getting cooked that in this case can be lived with because it does come back. So overall, for this example,
document.
So overall, this case study is quite successful because it gave the operator confidence in the drilling fluid systems, the fact that they could come back after shut-in, and also allow them to understand that if they have any issues in the future due to the shut-in, this is the mechanisms that are occurring. Moving on to the second case study. This was a batch drill example. We're slightly different here because we've moved straight on to the full sequence testing. So in this example, there was a drilling fluid applied. That was followed by a completion fluid to allow the sanding hardware to be inserted. So the drilling fluid applied, completion fluid. So just again, if anyone's unaware of the test cells, we would have the ability to put the hardware into the system whilst doing the core flood. So that gives an indication of how the hardware will perform. In this case, you can also do sand retention testing for the candidate sand screen to use, but the sand screen was selected prior to the study. Then a treatment fluid was applied. The wells were shut in, and then we went on to return to production drawdown as the previous. So this one was going to look at 3 weeks, 2 months, 4 months, 8 months, and 12 month shut-ins. So this case study is really, really key. The key point of this one was understanding the geology of the core. The reservoir core was available. We cut, cleaned, performed XRD and SEM prior to testing. As you can see on the left-hand side image of the SEM, we have the pink is not the potassium feldspar, it is actually the calcite. And that on the XRD graph is the burgundy color. And this, I'm just pointing this out because it's very important to this specific case study. So unfortunately, in terms of shut-ins, the shut-ins didn't actually occur. The samples all failed. The samples we performed the test sequences. We applied the drilling fluid, we applied the completion fluid, we inserted the hardware, we put the treatment fluid applied the treatment fluid as well, and then we shut in the samples at the pressure and temperature. After 10 days, and the first sample failed, and after 5 days, another sample failed. There's a sample failed at 9 days. So yeah, what had happened was that the samples popped in the cell, the cylinder deformed, and the test failed. So you're saying, why are you showing this? It's because it is an extremely good result. It actually allows you to understand that this sequence is not going to be compatible. So as you can see on the XRD graph, again, the calcite's burgundy. The BT and AT samples in sequence are related to each other. So you can see at the top one, the value of the calcite has decreased a huge amount, probably about 15–20% in the post-test XRD analysis of the near-wellbore. As you can see, again, that follows down for the second sample and then the third sample as well. And the fourth sample, not so much, but you can still see that's a decrease. So the calcite has gone missing from the near-wellbore. So what had happened was that the treatment fluid that was the candidate for this batch drilling was far too aggressive and attacked not just the drilling fluid constituents, but it actually attacked the matrix of the reservoir as well. So as you can see on screen, we've got 2 SEM images. You can see with the areas circled in white on the left-hand side, you've got areas where the calcite has been removed, the cement, and on the right-hand side, you can see a fossil. So not only did we have some calcite cement in the core, but we also had some fossiliferous material, calcite-based, which is obviously going to be part of the core structure. And when that gets dissolved, you're losing integrity. And unfortunately, that is what happened. But again, I say quite fortunately, because that knowledge of that treatment fluid being aggressive and attacking the matrix is now known, and other options could be looked at. So you might think, okay, you didn't get to see the whole shut-in, but the results were really important to understand. And yeah, that allows the operator to then go and say, well, is this something that you want to do? So mentioning that we had the screens in situ, as you can see here, the screens got blocked. So we did try and mobilize some of that, but yeah, as you can see that the screens have been, and you can even see a little bit of interaction with in the middle of the sample with the acid. So this is the advantage of testing a full sequence core flood with the shut-in. You get to see how the completions will react as well. What we did try and do to get some additional information out of the collapsed core, as you can see in the top, we have a micro CT image. What we tried to do is then use digital modeling, the pore network, to get the connected pore. So if you can see in the results here, we calculated the percentage stimulation, and when you can see that the numbers are huge. So the core was stimulated, the cement was gone, but also at the same time you had near-wellbore collapse. So again, what I really wanted to point out that this is, it may seem a bad result that you don't have the end product of seeing what's going to happen at 3, 6, 8, 12 months, but you do see that initially that chemical may not be what was expected. And then that allows the vendor as well to take that information and maybe tone down the reactive components of the treatment. So everyone wins in that understanding. If they hadn't done the laboratory testing for that acid and just turned on the taps, then I think in that case there's probably quite a lot of reservoir being produced. So the conclusions of the case studies that diagnostics and lab data is key to understanding what will occur whilst a well is shut in, whether it's a new well or coming back online, understanding how the treatment will work. It's key to experiment in the lab and not the field. The shut-in tests for case 1, as I mentioned, the initial effect on the shut-in period had an initial effect on production, but long term the values will come back as per the lab data. And then using the diagnostics, it was clear that there was some differences in how the core and the fluids had interacted. So that can be taken and noted for any future issues. Case 2, bad result, don't think so. It actually allowed greater understanding. The mud cake was definitely cleaned up, so that was good. But at the same time, you understood that the matrix was collapsing, so that means a less aggressive treatment was probably the best case for that. Conclusions, case studies for formation damage shut-ins for the 2 that I've decided today for the North Sea. Experimenting in the well, the outcome is unknown. If you get production coming on, great, that's really, really good and excellent news. But if it doesn't come back onto the production, you don't understand the mechanisms of why that's occurring. You could go in with the wrong treatment. The understanding is key. For emergency shut-ins, replicate the original drilling sequence. Experiment with different treatments in the lab, so you don't have to spend money trying different chemicals. If one chemical doesn't work and you have to go in with another one, you're spending a lot of money on man hours, different fluids, lost production. Shut-ins are not idle periods. Nothing stops. Chemistry continues. No matter what, the processes are ongoing. Fluids could separate out, like we mentioned before, fines could settle out, scaling might occur. So shutting in and just leaving and then thinking production is going to come back is not a viable option, in our opinion. Testing these things out in the lab makes a lot of sense. And on that note, that is the examples for today, and thank you very much for attending.
Okay, Leigh, thank you very much. That was quite interesting. Okay, and if just want to check if we have any questions. Don't seem to have any questions in the Q&A section. Chat. Okay, right. So giving the audience some time to ask any questions if there's any. Okay.
No problem.
So we have some that came in now. So what is the RPM used in the ultracentrifuging step, and how does it translate to the drawdown pressure? That's the first question.
The RPM is based on the drawdown pressure, so that we're replicating the pressure. So say, for example, it's 50 psi. I've not ever used a centrifuge, so I won't be able to translate the 50 psi into the RPM. But rest assured that the centrifuge spinning speed is matched to the pressure that is used in the drawdown. So we're not exceeding or underplaying that long-term effect. So it does replicate that long-term. So yeah, centrifuge speed is matched to the pressure of the drawdown.
Okay. Thank you. So next question is, what kind of damage do you think gets removed with spin down? Do you have a way to model that?
The spin down damage is generally retained filtrate from any drilling fluids, or in the shut-in case, it could be small fines that have been trapped in pore throats and then get mobilized. But yeah, with longer flow, then you're cleaning up more. You're potentially depleting, and then the filtrate then comes out. And then for the second part of that, the fluid that comes out of the core in the centrifuge is measured in terms of volume. So you have an indication of what's been removed. And if we see any, you can do fluid analysis if you expect that particle size analysis, if you expect any fines or anything to be seen there, and you can understand that part of the aspect as well. But the main cleanup met with centrifuge is the retained filtrate, and you get a very efficient sweep with using the centrifuge with the spin down.
Okay, all right, thank you. So another question is, how do you mimic 3 months or so in the lab?
So,
and how do you relate your rates to field values? Two of them.
Okay, so how we replicate the shut-ins in the lab is we obviously apply the chemicals, the operational sequence as per what the well's going to see or as it gone through. And then what we do, we have a special shut-in facility at Premier Corex in Aberdeen, where we take the cell, put it into the various ovens, and then incubate at static or the pressure that's required and the temperature. And then we literally leave it for 3 months if it's a 3-month shut-in at that pressure and temperature. So those chemical reactions that we were talking about that could occur are happening in the cell. And then once that 3 months is up, and obviously just we're monitoring that every day, making sure that there's no pressure fluctuations or anything like that. So we know that everything's going as it should. And that is how we worked out in the second case study that the samples were. I mean, obviously we saw that the pressure went spiked and went boom. And then we put we take the cells and then we put them back into the main system and then draw them down and do the other diagnostics. Sorry, Kareem, what was the second part of that question?
So the second part of the question was, how do you relate your rates to field values?
We can do an estimation in-house with the rates to the field values, but what is preferential is that the engineers or the project managers from the operator sides provide us with the rates. That way that we are not calculating or upscaling the rates as an independent lab. It's better to have an understanding from the operator what rates should be used. But we can calculate the rates as requested, but we prefer to have a more accurate supplied by the operator, mimic down.
Okay, thank you. So here's another question. So which post-test analysis do you think is most valuable? CT, dry SCM, wet SCM, what do you think?
I don't know. I think they're all powerful combined. I think if we're looking at drilling muds on their own, then probably you'll be mostly looking at solid mechanisms. So that's where the dry SEM comes into its power, looking at the solids. You're probably not going to have any interactions because there's only one fluid applied. So if you're just using a drilling mud in the shut-in, the SEM would be the most powerful tool, the dry SEM. When you're looking at more than one fluid in sequence and potentially using acid, if you're using a treatment fluid, the micro CT is probably the most powerful tool in that sense, because you're then looking at the differential alteration, and you could potentially see any dissolution that's occurred due to the acid. You'll be able to see where the cake's cleaned up, and that's a visual representation. If you're looking at potentially heavier oils, or you're looking at maybe a scaling treatment, you're suspecting that maybe a well's been shut in and you've identified that scale's been present, potentially in a replicated test that you've done prior to this, and you want to see how a scale treatment would work, then the cryogenic SEM is the most powerful. Because the cryogenic SEM is done with the sample being dirty, fresh. It doesn't go through any cleaning processes. So when you're looking at that under the microscope, you'll be able to see how much scale has been potentially dissolved, or you can see how much precipitate's actually occurred. So probably in different scenarios, each have got their own strengths, but combining them gives you the best overall intelligence on what's actually occurring. So yeah.
Okay. Interesting. Good answer. Thank you. So another question is, what about injection wells? Did you get to mimic gravel pack completion somehow with the core experiment?
Yeah, if you want to mimic gravel pack injection, no problem. The core holders that we have custom built have large annuluses, specifically designed to separate out that screen gravel pack zone against the core. So sorry for not including any examples of that today. If you get in touch, then we can look at that. But yeah, the mechanisms and the concept of the core flooding is basically the same, except you're going in the opposite direction. So yeah, if you want to investigate an injection well that's been shut in, or you're trying to re-inject, very important for CCUS, by the way, if you're going into an old well, understanding the mechanisms that have occurred. I mean, you might have residual mud cake that's not been cleaned if you're doing it an old production well, and then you're trying to inject CO2 through that, or carbon, sorry, through that, then yeah, that's where this kind of testing comes into its power with the injection. So not only does it have oil and gas causes or applications, sorry, then it comes into carbon capture as well. So yes, that is an important question, and yeah, an important point to make as well. So yeah, we can do that, mimic that, and yeah, it's important for CCUS, which is what the next topic is.
Yeah. So one more question is, what additional testing would you recommend if shut in is 5 to 10 years old?
Oh. I don't think anyone would want to shut in for 5 to 10 years in the lab. It probably would be budget smashing. We would recommend shutting in for as long as feasible. If the well's been shut in. That's a difficult one. I have been asked in the past about a well that was shut in for 30, 40 years. How will that perform when it comes back on? I don't know. What we can replicate is in the lab is as long as the project managers, the people in charge, want to mimic. And you can potentially extrapolate out what might occur if you do different variations. So say, for example, the second case study had been successful and we'd managed to do the separate steps. Looking at the diagnostics and looking at what the difference is in the reactions in each step. Say, for example, you had more baking, the cake got more compact and more solid over time from the 3 month, the 6 month, and 9 month, and the 12 month. You would expect then, if you extrapolate that over 5 to 10 years, you would expect that to continue. If you're seeing more formation of scale or reduction over time, you would expect that to continue. So if you do a stepped approach, then you can extrapolate and expand and say, well, if this is what's happening in this percentage over the 1 month, 3 month, 6 month, 9 month period, then that would be probably the best plan of action to try and replicate a longer term effect by then extrapolating the data from the various different lengths of shut-in.
Okay, right. So I have another question here, which I think touches on that one that you just answered. Was this case study showed a dramatic change in properties, but are the general takeaways on the impact or impacts of the shut-ins is in general? So are there any general takeaways on the impact of the shut-ins in general?
We've done several shut-in studies over the last few years. I picked these two because I think that they have different but positive outcomes in understanding what's occurring. We have done a shut-in study in the past where you visually saw with the lab results and the diagnostics that things did get worse over time, and they would stay that way. So yeah, not everything is going to be like a positive outcome from these two. You will sometimes see reduction and increasing over time, but that again is a result. It gives you the understanding of and the thought process of planting the seed of maybe going, is this something that we can live with, or is there something that we need to change? So again, understanding that I think is quite key. But yeah, as we kind of say quite a lot, every reservoir is different. Every fluid formulated is generally designed for that kind of reservoir tweaked. So not every well is going to have the same reaction, and it depends on the chemicals used as well in the sequence. So yeah, not these are two examples, but there are others with different outcomes. Yeah.
Okay, right. So I think maybe we've answered that question already, but just got posted again. So have you done this one? What kind of damage do you think get removed with spin downs? Do you have a way
We
to
did
model
answer that one. Yeah.
We did answer that one. Okay.
Yeah.
All right. Okay. Okay. So right, here we go. More questions coming in. Okay. So how confidently can core flooding experiments predict long-term well suspension integrity when field scale barriers, degradation mechanisms, cement aging, microannulus development, geochemical interaction, and pressure temperature cycles occur over years or decades, but laboratory tests occur over days or weeks?
Okay. I think we kind of touched on that with the 5 to 10 years. When we're doing these examples of the shut-ins to talk about the variations, I mean, if that was something that you wanted to mimic, we could probably change the temperature and pressure in the core to mimic variations. The cementing, that's more of an engineering point of view. So we've maybe got some more engineering aspects of that question than the laboratory testing will show. Over many years, we can only do in the lab what we can. So obviously, in our opinion, better to experiment in the lab in the field. And for those long-term tests, long-term suspensions, the staggered approach with the different shut-in times to extrapolate what's changing in those tests is probably the best way to replicate longer-term effects over years and years. Yeah, that was a long question, so I think I might have answered that, but if there's anything, please drop us an email. on that one, and we can get back to you. But I think for the engineering side of things, the lab testing is more on the production or the injection and the interactions with the core, rather than the engineering aspects of it.
Okay. All right. Okay, I think that's all the questions that we got so far. So to the audience, thank you very much for joining. Thank you very much for the interaction. There's a very interesting session. Leigh, thank you very much. Quite interesting. For all of you, thanks for joining again. We hope to see you again on our next session. You will get a copy of the recording to your emails shortly. And just as a reminder, our next session is going to be on the 5th of May. Our speaker is Ines Ahmed, who is our core analysis subject matter expert based in Houston. Ines will be talking about using lab data to de-risk CCUS projects with focus on utilization, which is quite an interesting topic. Please follow our LinkedIn page for more updates about our webinars and our activities. And also, our YouTube channel will have a copy of the recordings for this session and all the previous ones as well. Feel free to log in and check those out and subscribe if you are interested in our updates. Thank you all very much, and we hope to see you again. Thank you, Leigh.
Thank you. Thank you, everyone. Have a nice evening.
Okay.
Afternoon.
Thank you all.